We know that letters stand for numbers in algebraic expressions. Sometimes it's necessary for us to designate what numbers don't make sense in certain kinds of expressions. For example, if we're talking about the square root of x minus 3, and we know that x stands for any real number, we know that if x stood for, let's say something as simple as 0, we would have the square root of 0 minus 3, but the square root of negative 3 doesn't make any sense. So we want to restrict the values of x so that the expression makes sense for all of the replacements for x. Now, that restriction is simply a restriction on or a definition for the domain of our expression. The domain meaning, roughly, the acceptable replacements for x. Now, we understand that in a situation like this, we would like to be taking the square root of a positive number or 0, so we might come out to the side and say, gee, for what values of x then would we have positive numbers or 0? So we'd like to know what values of x will cause x minus 3 to be greater than or equal to 0. And adding 3 on both sides, we find x to be greater than or equal to 3. Aha! So x needs to be greater than or equal to 3 for that to make sense. And so we would designate that idea like this. We would simply say, comma, x is greater than or equal to 3. That is, this expression makes sense for all real numbers x for which x is greater than or equal to 3. Now, in a similar way, we might have a certain kind of restriction on the domain or some description of the domain in a problem like this. We know that we can't have denominators becoming 0. And the only value then which we would disallow in this fraction would be the value of x that would cause the denominator to become 0. This denominator is 0 when x is negative 5. So we have to disallow that value. We can say that x can take on any old real number in the world except negative 5. So we simply say something like this: x is not equal to negative 5. Now, this is just an idea of the domain or the description of an algebraic expression or an algebraic fraction. By the way, that last fraction is really a rational expression. A rational expression is just a polynomial numerator, polynomial denominator within a fraction. And we're going to talk about various operations on rational expressions. And the first operation is just one of reduction. When we reduce a fraction, a common fraction, we just take out common factors in numerator and denominator. Well, the same is true with algebraic fractions. That is, we're looking for common factors in numerator and denominator to eliminate or cancel. Now, to see those factors that are alike, we have to perform the operation of factoring in both numerator and denominator. Factoring up here, we get these two factors. Factoring down here, we get these two factors. All right, now we see that the x minus 2 factors can sort of take one another out. Now, we are allowed to do that because we can think about separating the factors in such a way that we have x minus 2 over x minus 2 almost as a separate fraction. And that's simply 1, you see. So we eliminate those factors, and we're just eliminating 1, sort of, and we're left with this as an equivalent form of that. Well, it's almost equivalent, and I'll talk about that in a minute, but we take these out and we have x plus 6 over 3. Now, the 3 and the 6 can't cancel because although there is a 3 factor within 6, you see, that 3 factor in 6 is not a factor of the entire numerator. It's a factor only of that term of the numerator, and so it's not a candidate for cancellation. We have to be talking about factors of the entire numerator and denominator in order for canceling to take place. Now, we have to be kind of sensitive to this domain idea, and if we're talking about equivalence here from one step to another, that is, this has the same value as this and this and this, all the way down when we simplify in expressions, we have to make sure that any restrictions on the domain that appear here have to appear here. And we have an implied restriction on the domain by the nature of this denominator. That is, there is a value of x that will cause this denominator to become 0. And that's the restriction restriction on this domain. Now, a lot of times if it's evident, if we can see the fraction and see the values that x could take on to cause the denominator to be 0, we don't actually actively write them on the side of the fraction. We did that before, but we don't always do that. But if we have a cancellation like this, it's not even evident what the value would be for x that would cause the denominator to become 0 up here. So I can see that value right here very easily. If x takes on the value 2, then this denominator becomes 0. But that x minus 2 canceled, and so it's not really self-evident what the value was that would cause the denominator to be 0, so we actually have to say that here. X cannot be equal to 2 for this to be equivalent to that. All right, here's another one. Same idea now. There's a little trick in this one, a little nuance that I want to show you. Notice that the numerator is not in standard form. And when we factor, we get these two factors for the numerator and these two factors for the denominator. And here's what should jump out at us. We have 4 minus x here and x minus 4 here. We almost have a cancellation opportunity. And we would if we could accomplish a sign change. Now, the relationship between these two is a little more evident if we do this. This is 4 minus x. If I write minus x plus 4, that's the same thing as this. Let me put it in that form just for demonstration purposes here. This is minus x plus 4. I just changed the order of the two numbers in here using the commutative property, but I wanted to do that because it's pretty easy then to see that we have a sign change for both of those terms in parentheses. And if I could get them to change somehow, then I'll get a cancellation. Now, I can accomplish that sign change by forcing the factorization of -1 in either numerator or denominator. That is, I can take this numerator. By the way, I could write this as x plus 3 instead of 3 plus x. It really doesn't matter. But I'm going to force the factorization of a negative sign. And really, I'm taking out -1. You see, I'll write it. I want to write it like that. I could just put a minus sign here, and that would probably be okay. But I'd rather do that at the beginning of a listing of factors. I'll put -1 here because I'm kind of within this list of factors. But when I take out this -1 factor, it'll change the signs here, so I'll have x minus 4. And now I have the cancellation opportunity that I was looking for. So these can go out. And now this -1 can multiply throughout this other factor. So I'll have minus 3 minus x, or minus x minus 3 like this. And in the denominator, I have 2x minus 1. Now, you can leave it in factored form if you want to. That's probably still not incorrect. It is important, though, to be able to recognize the different forms that fractions can take, because there's going to be an answer in the back of your textbook, and if you're checking your answers with the answers in the back of the text, you have to know when you have an equivalent form. Okay. Now, we had a cancellation here, and therefore we have a restriction on the domain that needs to be listed down here. When x is 4, this factor becomes 0, and the denominator therefore becomes 0, so we have to write that restriction down here. X is not equal to 4. In this next problem, we're multiplying a couple of algebraic fractions. And it's important to realize that multiplication of algebraic fractions is handled in exactly the same way as the multiplication of common fractions. That is, we multiply numerators times numerators and denominators times denominators. The only difference is, or the big difference is, that cancellation opportunities are very important to take advantage of early on in the problem. Otherwise, you get a really long-winded polynomial numerator and denominator that's reducible, but you can't see the reduction. So the idea is to factor and look for those cancellation opportunities early on. So we're really just factoring everything in sight. Factor every numerator and every denominator and look for those cancellations. So here we would factor this numerator into these two factors. Factor this denominator, it comes to these two factors. Factor up here and we get this. Now this would probably take 2 steps because we have a common factor of x that we take out first. And it's x times a trinomial, and then the trinomial is factorable into these two binomial factors. Then the denominator is factorable into this. Okay. And by the way, while I'm thinking about it, from time to time, when you see problems, when I present problems up here and you see a problem you think you can work on your own, I suggest that you actually copy the problem down and try it on your own. Just pause the tape or stop the tape and try the problem on your own and come back and roll the tape to verify that your answer is correct. And this practice idea and this hands-on thing is a real big help in transferring information from short-term memory to long-term memory. That's the whole purpose of doing homework. All right, at any rate, we're looking for cancellation opportunities here, and we're looking for factors that are in any numerator to factor with factors in any denominator. That is, we have this 2x minus 3 in this numerator. Well, it can cancel with this 2x minus 3 factor in this denominator. So those two can go out. And then we have, let's see, is there an x plus 5 up there? No, there's not. The x minus 1 with this x minus 1 can go out. We have this 2x. Well, let's see, the x is a factor, and that's an x factor. So those x factors can go out. And now what do we have left? We have x plus 2 times x minus 2 for the numerator, factors that haven't canceled. And in the denominator, let's see, we have 2 times this x plus 5. So we have this. Now, the restrictions on the domain, or I guess the challenging part, if there's any challenging part here, it would be the values of x that will cause each of these canceled items to become 0. Now, this factor x becomes 0 when x is itself 0. So x cannot be equal to 0, or else it wreaks havoc in our situation here. So x can't be equal to 0. This one is rather self-evident too. If x is 1, then x minus 1 becomes 0, and therefore we'll have a 0 denominator. So x can't be equal to 1. Now, it's not quite as evident, the value of x that will cause this factor to become 0. And when it's not evident, then what you can do is set up a little equation like this. You're asking yourself, what value of x will cause 2x minus 3 to be equal to 0? Add 3 on both sides, divide on both sides by 2, and you find x to be 3 over 2. So x cannot be equal to 3 over 2. That's how you identify it, though. You see, if you can't see through it very, very quickly. Okay, that's the idea. Division of algebraic fractions is handled in much the same way as division of common fractions. And you recall that what you do is you change the division problem to a multiplication problem. That we change the sign to multiplication and we flip over the second fraction. That is, we multiply by the reciprocal of the second fraction. So we just flip this rascal over when we change the sign to times. Now, at the same time, or not necessarily at the very same time, but we're thinking about also factoring, because when we multiply algebraic fractions, we have to look at factors. So the tendency is to try to flip over this second fraction and factor at the same time. Now, that's it's kind of a risky situation when the fractions become very complicated. Here, it wouldn't be very difficult at all, but in some situations, it becomes difficult. And in those situations, I suggest you resist the temptation of trying to do both things at once. At any rate, we have the factorization of this becomes that, of this becomes that. Now, notice that this is a perfect square trinomial because it factors into a binomial times itself. This is the difference of squares, which factors into the sum and difference of the same two terms. And they happen to sort of correspond with these guys up here. Anyway, we have x plus 7, and then the 3 comes out of those two terms to give us this. And we have cancellations all over the place. We have the x minus 7s going out here. This x plus 7 goes out with that x plus 7. This x minus 7 takes out that x plus 7. Now, all the factors have disappeared in these numerators. So what's left when we cancel these is simply a bunch of 1s. We generally don't write them, but really there's just a 1 factor left when these cancellations occur. So it's 1 times 1 times 1, or simply 1 for the numerator. And downstairs we have 1 times 1 times 3 times 1, or simply 3. So this reduces to 1/3. And now we have to talk about the restrictions. Well, we're talking about values of x that will cause any of these original denominators, you see, to become 0. And we would have, we restrict x to, we say that x can't be either plus or minus 7 because of this situation right here, and that covers us for the other situation as well. So x cannot be equal to plus or minus 7. Before we leave this segment, I think it's important that I mention something more about this idea of limiting the domain or stating the limitations on the domain. Back in this particular one where we had a lot of cancellations, Now, those cancellations led to these limitations on the domain. But you know, I didn't say anything about x not being equal to -5. And because an x of -5 would cause this factor to become 0, and therefore it would be disallowed. I don't mention that over here. But it's sort of self-evident from the nature of this factor within this denominator. So if it's self-evident sort of from the fraction, we don't need to mention it as an extra item over here. It's just that we have to mention those items that have been omitted or have been canceled that are not self-evident in the fraction that remains. That's the idea. As you might expect, adding and subtracting algebraic fractions is handled in exactly the same way conceptually as you would add or subtract arithmetic fractions. We need a common denominator to add and subtract, and once we have the common denominator, we add or subtract numerators. Now that's the good news. The bad news is that some of these problems can become rather algebra intensive. That is, we have a lot to keep track of, and organization will play a big role here. Here we're adding a couple of algebraic fractions. We already have the common denominator, so we simply add the numerators, and as we would expect, we just bring down this numerator and show the addition of this one. And we have our common denominator under that big numerator. Now it's just a matter of collecting like terms. 2x minus x is x, and the ones go out, so we have x over x plus 3. Now here's one of the most common errors in this situation. Suppose I just change this to subtract. Now, I want to subtract this binomial, and it's really important that you add parentheses here to show that you're subtracting both of those terms and not just the first one. The common mistake is to do this, is to just put minus right here and then think that you're done. But really, you are subtracting all of this, and it's like minus everything in parentheses. So both signs have to change, and this is the result of that situation. And now we would be collecting like terms. So be very cautious in this circumstance when you have a minus sign. In fact, you can set it up a lot of different ways to be successful, but just take a lot of care with it. Another way to set it up is like this, is to say, okay, I've got the 2x minus 1, and I'm going to subtract the 1 minus x. You see, just burn a step to show what you're doing here, and then in the step after that, you would have the 2x minus 1 minus another 1, and then plus x, excuse me, for the numerator, and then the denominator x plus 3, and then collect like terms, and you have your answer. Here's one that's a little more complicated. We don't have common denominators here, so we have to rewrite the fractions with common denominators. Now, in order to identify common denominators, we have to be looking at factors, because the common denominator will contain every different factor that we see in any denominator in the problem. So we need to go through a step and factor. Factoring here, we get these two factors, and we just bring this down because it's already in a relatively factored form. All right, now, every different factor that we see will be part of the common denominator. We see x plus 2, that's part of the common denominator. We see x minus 1, that's part of the common denominator. We see x plus 2, oh, it's already there because we identified it over here. So our common denominator is just this product. And often it's valuable to like go out on the side and actively write it down. Our common denominator is x plus 2 times x minus 1. All right, there it is. Now we can refer to it then if we write it down somewhere. Now we'd like to rewrite these fractions so that they have this common denominator. This one is okay. It already has that common denominator. That one's not okay. It's missing the x minus 1 factor. And in order to get that x minus 1 factor into this denominator, we're going to multiply it in. But if we multiply x minus 1 into the denominator, we have to multiply x minus 1 into the numerator as well, because we need to be multiplying by a form of 1. All right, so that's the idea. Now, once we've done this, let's see, 1 times x minus 1 is x minus 1. Now we have our fractions have common denominators. We can collect the numerators. We have the subtraction then of this numerator. We have to be very careful. So we have minus x plus 1, you see, and x minus x will go out, and then the plus 1 will take over, so it's 1 over our common denominator. Now, some of these problems like this can look really simple, but become rather algebra intensive. And as I mentioned before, organization plays a big role here. Let me show you a problem that is of that variety. This looks relatively simple, but let me show you how it gets complicated very quickly. Now, not complicated in the sense of difficulty of understanding or anything like that. Complicated in the sense of organization. It gets messy very quickly. All right, our first thought here would be to identify a common denominator. To do that, we have to be looking at factors. Now, we're already in a factored form here. We're already in a factored form here. Difference of squares, factors. Okay, good. Now we can identify a common denominator. The common denominator contains every different factor that we see. We see an x minus 1, so x minus 1 is part of that common denominator. We see x, so x is part of that common denominator. We see x plus 1. X plus 1 has to be part of the common denominator. We see x minus 1. Oh, it's already here. Now, you might be thinking, what happens? When is it that we have more than one factor of a certain type? Well, if you have multiple factors of something, like if we had here x minus 1 cubed and x minus 1 to the first power here, we would take that like factor the most number of times that we see it. So x minus 1 cubed would be part of the common denominator. We need 3 factors of x minus 1 as our common denominator. Okay, we don't have that here. We're not going to worry about it. Now, we've got this is our common denominator. We need to rewrite those fractions so that they all have this common denominator. Now, to do that, we're going to just inject those missing factors into the denominators, and therefore we need to inject them into the numerators as well, the missing factors I'm talking about. This denominator has the x minus 1 factor. We need to pop in an x and an x plus 1 factor. So we're going to take this fraction and we're going to multiply in the x times x plus 1 over x times x plus 1 and multiply that into the 3 over the x minus 1, like that. That's what we're doing. Now, this one is missing the x minus 1, x plus 1. So, let's see. Now, in between that minus sign and this fraction, I'm going to pop in those missing factors in both numerator and denominator. So I'm just going to write x minus 1 times x plus 1 over x minus 1, x plus 1, like this. Then 2 over x. You see? So the missing factors are going in between the minus sign and the fraction. That's all there is to it. It makes it kind of simple. Now, I'm stringing things out here. We have an awful lot to keep track of, but it's really not any big deal if we just maintain concentration. Here, this one's missing the x factor, so we're just going to multiply x over x times this fraction. So this is what we have. Now, let's march back over here and perform some calculations. In the numerators, we want to multiply out the numerators. We want to string them out. We want the expanded form of the numerators. And that's because all of the numerators are to be collected. So we want all of the separate terms within those numerators to be self-evident, to be evident and not in a factored form. On the other hand, the denominators can remain in factored form because it's only at the end of the problem that we may have an opportunity to cancel. And to see the cancellation opportunities, we have to have a factored form. So we'll leave the denominators in factored form. In the numerator here, we have 3 times x plus 1. Now, that's 3x times x is 3x squared. 3x times 1 is 3x. And all of this is over the common denominator. Now, in the interest of time, I'm going to put CD for common denominator. All right, then over here we have minus. All right, now we'd like to multiply all this out. This is x minus 1 times x plus 1 is x squared minus 1. So this is x squared minus 1 times 2. Now I'm taking a little bit of a mathematical risk here by combining steps. And if I were doing this on paper, I wouldn't combine steps like this, but in the interest of time, I'm going to do so here. So really, this is x squared minus 1. That's what I'm thinking about. You see right here, 2 times x squared minus 1 is 2x squared minus 2 over our common denominator. And then we march over here, plus And now I'm thinking x over x times all of this. Parenthesis will help us with the multiplication in the numerator. X times x, x squared, and x times 3, 3x. All over the common denominator. Now we want to go through and collect the numerators. So let's see. We have this first numerator, the 3x squared plus 3x. And we have minus this. Now here's what I recommend you do. Well, maybe I ought to tell you what I recommend that you do not. You do not want to try to collect by just looking at these numerators as you see them now. You want to write down all of the terms that are in the numerator of the overall fraction that you're going to have as you bring these together. So you write the 3x squared, the 3x. Don't bring anything together, and then you'll write this. I would put a parenthesis here just to help the thinking, and it's minus all of this, so change the sign. So we have minus 2x squared and then plus 2. And then for this, it's plus these terms, so it's plus x squared plus 3x. And now all of this is over the common denominator. And now we're ready to make a big collection here. Let's see. The terms that are squared, I have 3x squared minus 2x squared. That's 1x squared. Plus another 1x squared, that's 2x squared. So I'm going to pop a 2x squared into the numerator, and I need some room, so I'm going to come out here. So in the numerator, I have the 2x squared. Now let's march back over here. I've already collected the x squared terms. Those are out of here. Now the terms involving x, 3x and 3x, that's 6x, and then I have a 2. So 6x plus 2 are the other terms in the numerator. The denominator is the common denominator. And I think what I'll do now is factor in the numerator as much as possible to see if I have some cancellation opportunities. I see a common factor of 2, and I snag the 2 out, and I have x squared plus 3x plus 1. And I can't factor this trinomial any farther, so I'll bring down my common denominator, and I'll actually write it down. I have it written down over here, so I can just refer to that. I've got x times x minus 1 times x plus 1. And no other cancellations are possible, so this becomes my final answer. This next example involves fractions within a fraction. And when you have that situation, it's called a complex fraction. There are actually two strategies for dealing with complex fractions. I'm going to show them both to you. One strategy is this. Now, for emphasis here, it's the idea that all of this is the numerator of an overall fraction, and here's the denominator of that fraction, and here's the big fraction bar. And within the numerator, there's a fraction. Within the denominator, there's a fraction. If one or the other of these or both happens, then we have a complex fraction. Okay. One strategy, generally, is to manipulate into a situation where we have a single fraction in the numerator and a single fraction in the denominator, the big numerator and big denominator I'm talking about, and then think about a fraction implying a division problem. That's what we're going to do here. We're going to bring these two together into one fraction. Well, to do that, we have to have a common denominator. The common denominator is x, so we'll multiply the 3 times x over x. Here's what I'm thinking. I'm going to take this parenthesis out, but I'm multiplying this by x over x. Now remember, this is 3 over 1. So it's 3x in the numerator and 1 times x in the denominator to get this. In a similar way, the 1 is multiplied times the x minus 1 over x minus 1. So x minus 1 over x minus 1 times 1 is x minus 1 over x minus 1. And then we just bring this down. Now notice I'm working with both a numerator and a denominator here. I have really two problems in one that I'm having to deal with, and I'm just kind of jumping back and forth. And that's the difficulty with this kind of problem, that you just jump shift your thinking from one to the other. But a little bit of concentration takes care of that quite easily. All right, we have up here, we have 2 minus 3x over the common denominator x. So 2 minus 3x over x. Up here, we have x minus 1 minus 1. So that's x minus 2 over this common denominator. Now, we have this divided by that. So let's just write that down. Write it as we understand it. We understand numerator divided by denominator. So it's 2 minus 3x over x divided by x minus 2 over x minus 1. All right, then the division problem becomes a multiplication problem as we flip this over and we multiply as we understand, 2 minus 3x times x minus 1, and in the denominator x times x minus 2. Now, you notice that I have the caveat here of x is not equal to 1. We're not going to belabor that point very much, but to be technically correct, I need to write that because it's not self-evident from this. And yet, it is self-evident from the beginning. That is, if x were 1 right here, this denominator would be 0, and it would cause this to be undefined, and the whole problem would be undefined. And it's not self-evident down here, so we have to write it. Okay, that's the idea. Now, let's look at the other technique. This technique has quite a bit of manipulation involved in it. And sometimes when the fractions get complicated, it can be really messy. The other strategy is to do this, is to identify sort of an overall common denominator involving all of the fractions that we see within the complex fraction. That is, I have a fraction here and I have a fraction here. Now, between those two, let's identify a common denominator. That common denominator contains every different factor that we see. We see an x and we see an x minus 1. So x times x minus 1 is that common denominator. And conceptually, here's what we're doing. We're just going to take this fraction and we're going to multiply it times. We're going to take that common denominator and multiply it into both numerator and denominator. You see, we're just doing this. Now, I'd probably put this in another step ordinarily, but because I have a lot of board to work with, I'll just pop it in right here. You see, now this is a form of 1. So I'm multiplying that times this, you see, and times this. So that's the idea. Now, there are a couple of ways to proceed here. I can think about multiplying this times each of those two terms, but the manipulation goes like that. In fact, let's do that. Let's think about that. I'm multiplying this into this numerator, and so I'm thinking about I'll just use the distributive property. You see, to distribute it through those two. And then minus x times x minus 1 times 3. Now notice the minus sign and the 3 here. I just put this right in between those two. All right. And then in the denominator, it's a very similar idea. It's this times each of those two. So it's now just look for cancellation opportunities and let everything kind of sort itself out. We have this x cancels with that one. And we have x minus 1 times 2. So that's 2x minus 2. And then here we just multiply this out as minus 3x times x is minus 3x squared. And minus 3x times minus 1 is plus 3x. And then in the denominator, this x minus 1 cancels here. That's really what we were after. Back over here, we have x times x minus 1 times 1. X times x minus 1 is x squared minus x. And then here we have minus x times 1. That's minus x. And let's do some collecting here. I only have one squared term. So I have minus 3x squared. Then 2x plus 3x is 5x. And then minus 2 is minus 2. And then in the denominator, let's see, I have x squared, then minus 2x. And I'd like to factor if I can. Let me see. I believe I have a factorization opportunity in this numerator. You know, I can probably see through the factorization. In situations like this, I would take out the minus first of all. Now, we haven't really talked a great deal actively about this, but it's a manipulation that you can apply anytime you have a leading coefficient that's negative. So I would do this. I would say, okay, I don't want to deal with it in this condition. I want to write it like this. Now, all the signs will change. And I have this. And then the denominator, we have a common factor of x, so it's x times x minus 2. Now, it's going to turn out that the factors here are, well, let's see, minus, and then I'm factoring this into the product of a couple of binomials, and it turns out to be, I think, 3x minus 2 times x minus 1. 3x times x is the 3x squared, and the minus 2 times minus 1 is plus 2, and minus 2x minus 3x is the minus 5x. Okay. And then in the denominator, we have the x times x minus 2. Now, often these problems come out a little simpler than this, especially if you have a lot of fractions in the original problem. You get cancellations all around, and then things fall out rather quickly. But at any rate, notice that this is the same thing as that. And it is important to notice that they are. Notice the only change is in the numerator. We have the x minus 1 factor here. But the negative of the 3x minus 2 is the same thing as 2 minus 3x. So these are indeed exactly the same for both methods, as we would expect. It may surprise you to know that complications within calculus fall into the category of algebraic manipulation usually, and in fact more often than complications that are of a conceptual nature. The concepts within calculus are pretty easy to understand, but when you get into the manipulative part of it to implement those ideas, it becomes a little complicated. Now, authors of textbooks have come to understand that we can learn about those manipulations in algebra in order to prepare us for those complications that are going to come up in calculus later. And I want to show you a couple of techniques here that fall into that kind of category. Here's a situation where we have negative exponents, and those negative exponents can be dealt with like this. Our sort of traditional way of dealing with it would be to say, okay, negative exponents tell us we have misplaced bases, so let's see, the base of this negative exponent is the x. We'll pop the x into the denominator like this. So we'll do that here. We'll do that also over here with this term. Now we'd like to bring the two terms together. And it's a little bit tricky in some situations. In this one, it's not too hard if we think, well, gee, we have to have the same exponent here, and we can multiply in order to create that exponent by just multiplying this one by x over x. It's pretty easy to see because we think of this x as 2 over 2. You see, 2 over 2 plus 3 over 2 is the 5 over 2 here, and in the numerator it's simply 2x. In other circumstances, this part of it might be pretty complicated. But at any rate, since we have common denominators, we bring together the numerators, and here's a simplified version. Now, that's the way we would, at this point, deal with a problem like this. Here's another way to deal with it. We could actually take the same problem, and we could identify the smaller of the two negative exponents. Now, the smaller of these two negative exponents is this one, and we could actually factor this factor out of these two terms. You see, now we're going to pull x to the negative 5 halves out of these two terms. When we pull x to the negative 5 halves out of this term, we're left with 3. Okay, when we pull x to the negative 5 halves out of this term, wow, what are we left with? Well, think about the technique for general factorization, or taking out a common factor, and we'll get an understanding of what's going on over there. You see the subtraction there, but here's why it works. If you have something like, oh, let's say x cubed plus x to the 7th power, and you're going to take out the x cubed, the smaller, you see, of the two exponents, then when you pull x cubed out of this term, you're left with 1. When you pull x cubed out of this, you have x to the 7 minus 3. You see, think about subtraction of the two exponents to identify what's left over there. So it's this as expected. Now, what I've done here, this is simply this exponent minus that one. So using that idea, we have this exponent minus that one. You see, the one that we're kind of factoring out. So now we have minus negative 5 halves is plus 5 halves. 5 halves minus 3 halves is 2 halves, you see, or simply 1. So we have 3 plus 2x in the numerator, and this then is the only factor that needs to be kicked down into the denominator. You see, so we get the same result that we did before, and this turns out to be I shouldn't say more efficient, but it's a different kind of efficiency. And sometimes it's much more efficient to use a technique like this in calculus. Here's another situation where we can use a little bit of creative manipulation. Now we notice that 4 minus x squared is the same in all three of the terms involved in this big fraction. Now, this negative exponent means that this base is misplaced. It would mean that we would have x squared over 4 minus x squared, you see, to the 1/2 power as a fraction right here. Well, to deal with this situation, one technique is to say, all right, let's multiply through this fraction by a form of 1 that will clear the negative exponent. Okay, we can do that. The form of 1 that we're after then would be a, let's see, it would be this base to an exponent, which when added to that one would give us 0 for the exponent. And that would be 4 minus x squared to the 1/2 power, because 1/2 minus 1/2 is going to be 0. So now if we multiply that in the numerator, we have to multiply it into the denominator. Now realize that we are really taking this fraction, this form of 1, multiplying times that fraction, and I have to think about it like this, because this is being multiplied times each of those two. All right, now we have these common bases, or this binomial is the same, so all we're doing is manipulating exponents. So 4 minus x squared to the 1/2 times 4 minus x squared to the 1/2, we're adding the exponent, so it's 4 minus x squared to the 1 power. And then, as expected, the 4 minus x squared to the 1/2 times this business gives the 1/2 minus 1/2 to the, giving us 0 as the exponent on 4 minus x squared here. So we get this. And that's just 1. All right, that's just 1. And then in the denominator, we have 4 minus x squared to the 1/2 times 4 minus x squared to the understood 1. Adding the exponents, 1/2 plus 1 is 3/2. So that's why the 4 minus x squared to the 3/2 appears here. And then cleaning up a little bit in the numerator, this virtually goes out. It becomes a factor of 1 here. So we have 4 minus x squared plus x squared. And then the x squares go out. So we have 4 over this business as the simplified form. So it's a rather interesting kind of manipulation. This fraction is referred to as a difference quotient in calculus. And sometimes the manipulative process that's necessary is to rationalize the numerator. If we rationalize the numerator here, then it means to remove the radicals from the numerator. And when binomials are involved in that process, you may recall that we multiply by the conjugate. So here we would be multiplying by, now the conjugate, same binomial with a different sign, so it's the square root of x plus h plus the square root of x. And in the denominator, the same business. And some really nice things happen when we multiply conjugates like this. They're not nearly as imposing as they may seem. You multiply conjugates and you get the difference of squares. So it is the first item squared minus the second item squared. And that's really all there is to it. In the denominator, it's h times that binomial. So that's all I've written here. Now, squaring the square root gives us the radicand. Squaring the square root gives us the radicand. The x minus x go out, and we have h over all of this. The h's go out. We have 1 over root x plus h plus the square root of x.